Welcome back, Night Owls. This is Dr. Nighttime. And tonight we're continuing along with the LTAM course. And we're getting into Chapter 3, Life Tables. So let's begin with just what a life table looks like. Got a large number of columns, and I'll go through what these are a few at a time. First thing you'll see is L sub x is the number of people alive at age x. You assume some radix. A radix is some number of people you started out with, essentially. Here the radix is 100,000. You started with 100,000 people alive at age 20. This x is your age. Notice you have the x column on the left and the same x column on the right. Purpose of that is just that when you're looking all the way on these E columns, you just have to look across here rather than needing to track all the way back to here with your eyes. Alright, so L sub x is the number of people alive. Now, some life tables will also have D sub x. If L sub x is the number of people who lived to some age, D sub x is the number of people who died during that year. So you get the relationship L sub x minus D sub x equals Lx plus 1. Now, this life table, by the way, is the one that they give you officially on LTAM. They don't have a D sub x column. Instead, you would just have to do, if you needed D sub x, you do L sub x minus 1. Sorry, you do L sub x minus L sub x plus 1. Lx minus Lx plus 1. That gets you dx. Right. Also, yeah, I did mention I is the interest rate. Right? They do specify an interest rate I. Now you might think, what does interest have to do with living? It doesn't, but most of these columns will have something to do with finance, and I'll actually describe what those mean right away, even though we won't be using them until chapters 4 and 5. One last thing, by the way, this QX, right? We know what QX means, right? We covered that in chapter 2. It means probability of dying this year, given that you survived up until the beginning of this year to begin with. So you could also say that's dx over Lx. A few things that shouldn't surprise you. Lx decreases as x increases. The no zombies condition. Also, Qx increases as x increases. For the most part. It could be argued that for x between like 20 and 25, maybe you're still near the top of the accident bump or the recklessness bump. This life table doesn't assume that, it doesn't seem, but you could argue that. It's probably part of why they start x at 20. They just kind of cut off the recklessness bump early and say, well, we'll move on from there. Anyway, some more notation. A double dot x is the expected whole life annual annuity due value. So you might recognize A double dot as annuity stuff from exam FM, right? You see the double dot and you say, oh yeah, I think that means payment is at the beginning of the year, and it is, right? And you might also remember that annuity due means paid at the beginning of the year, and annuity immediate means paid at the end of the year, even though it sounds like they would be the opposite. But no, it's annuity due. But you might start thinking, well, wait. Okay, you mentioned that the next couple columns had to do with finance. I see what annuities have to do with finance, but what do they have to do with life? Well, in exam FM, all the annuity stuff you looked at, they said you'll get this amount of money for this number of years. and that was the end of it. Here, instead, we want to talk about, instead of getting money for some fixed number of years, we want to talk about getting money until an X-year-old dies. If you remember, with that annuity notation, you had the angle or the half box around the number. Here you don't. With annuity notation and also with insurance notation, a number without the angle around it means this is somebody age X years old, and it's payment until that person dies. A number with an angle around it means payment until that many years pass. So looking back at the table, A double dot sub X obviously should decrease as age increases, because you've already lived some amount of time, so you've already received some payments, and mortality increases with increasing age. I guess it's really the mortality increasing with increasing age that's the bigger deal. But it should be no surprise that A double dot X decreases with increasing age. What about big AX? That's the expected fully discrete whole life insurance value. By fully discrete whole life insurance, that means payment is made at the end of the year of death, regardless of when you die. There's no term limit on it. By fully discrete, we mean end of the whole year. And this pre-super 2 A sub X, I'll call this squared A sub X. That's the expected square of the value of a $1 insurance policy. Notice this also means expected value of a $1 insurance policy with double the interest rate. Sort of. The moment that I actually declare a currency here, dollars, the square of that value should be measured in square dollars. And if I were to convert from dollars to cents, I'd have to multiply by 10,000, not by 100. Whereas if it's a fixed sum and just twice the interest rate, according to the dimensional analysis, it should still be measured in dollars. And if I convert from dollars to cents, it would be multiplied by 100, not 10,000. That's a really nitpicky difference. But you should know that if we ignore, the currency itself and just say value of 1, then the expected square of the value is the same as the expected value if the interest rate were twice what it actually was. Now, why do we care about the expected square of the value? So that we can find the variance of an insurance benefit. Why don't we care about the variance of an annuity? We do. There are ways of calculating it that we'll get into in Chapter 5. Don't worry about that yet. But if we look back at the table, that explains what these columns are, or these 3 columns. Should be no surprise that A double dot sub X decreases with increasing age. Big A sub X increases with increasing age, from 5 cents on the dollar, more or less, to like 12 cents on the dollar from age 20 to 40. I should point out, the actual table they give you is 2 pages long and goes from 20 to 100. I didn't want to squeeze all that into one little slide and have you squint at your computer screen to try to read anything. But here are just the values over this time window here. these next four columns, where you have both a number without an angle and a number with an angle, what does that mean? Well, if you remember when we were talking about curtailed expectation of life and complete expectation of life, we said that x colon angle n means stuff happens until an x-year-old dies or n years pass. For annuities, this means payments stop after n years even if the person is still alive. For insurance, this means after n years, you make the payment, even if the person is still alive. There's other notation for if the insurance is a term insurance. We'll get to that in Chapter 4. The name for this sort of insurance arrangement, where if you survive some amount of time, you just get the payment whether you live that long or not, that's called an endowment insurance, because an endowment, or pure endowment, is an agreement to pay some amount of money conditioned on the person surviving to the appropriate time. So, looking back, these four columns, you'll notice AX colon angle 10 is less than, or sorry, A double dot X colon angle 10 is less than A double dot X colon angle 20, which is less than A double dot X. Because obviously, if you're limited to only 10 maximum payments versus 20 maximum payments, versus as long as you live maximum payments, the value will increase. But also, as you get older, the expected value of those payments decreases. Meanwhile, for big A sub x, big A sub x colon angle 10 is greater than big A sub x colon angle 20, which is bigger than big A sub x. Because this doesn't mean that payments just stop after 10 or 20 years. This means you automatically get payment within 10 or 20 years. Getting payment within 10 years is worth more than getting payment whenever. The last three columns are these E columns, 5EX, 10EX, and 20EX. Those are the expected values, expected present values of pure endowments. That is, you'll get a payment of 1 if you survive 5 years, 10 years, or 20 years. Notice that 5EX is worth more than 10EX, which is worth more than 20EX, for two reasons. One, there's a chance that you'll die more than 5 years from now, but less than 10 years from now. But also, even if you're guaranteed to survive, 5 years of interest is less of a big deal than 10 years of interest, which is less of a big deal than 20 years of interest. So 5EX is worth less than 10EX, which is worth, 5EX is worth more than 10EX, which is worth more than 20EX. Then as the person gets older, the older you get, the less likely you are to survive 20 years, or 10 years, or 5 years. So for older values of x, the endowment columns start to be worth a little bit less. So, as an example problem, given the following table, find 5Q25 deferred 5 years. Alright, so when you see 5Q25 deferred 5 years, you say, I'm thinking about someone who's currently 25 years old, and you want the probability that this person dies between ages 30, 5 years from now, or I guess deferred 5 years, and 35, 5 more years after that. So you'd say, I'm looking for L sub 30 minus L sub 35 over L sub 25. Plug in the numbers from the table. You can go back a few seconds to look at the table I just had up, confirm these numbers, and get the 5-year deferred death probability of 0.00171. Okay, so that's the sort of thing you would do if you're just looking stuff up in the table. But obviously it's never going to be quite that easy. They're always going to make it at least a little harder than that on the LTAM. What if they ask about some fraction of the way into a year? There are two main sets of assumptions they would ask about. The first is called uniform distribution of deaths. That means that in between integer ages, you're as likely to die in, say, January of that year as you are in August of that year, or December of that year. Notice this means f sub x is piecewise constant. And it gets us the formula that L sub x plus epsilon, where x is a whole number of years and epsilon is the fractional part. L sub x plus epsilon equals L sub x times 1 minus epsilon plus L sub x plus 1 times epsilon. And epsilon qx is epsilon times qx. So that if you're looking halfway in, you'll just say, great, the number of people who survive halfway through is just halfway between those who are alive at beginning of year and beginning of next year. And probability of dying in the first half of the year is just half of the probability of dying that year. So as an example, what if I had to estimate 2.6p 30.2 using UDD? UDD being uniform distribution of deaths. So I look, I say, I'm starting with someone who's age 30.2, so that means I take 20% of age 31 and 80% of age 30, and average those together. And I'm looking for what happens when that person, 2.6 years later, is 32.8. So 20% of age 32 and 80% of age 33. Crunch these numbers together, look them up in the table, do the arithmetic, and you get a survival probability of 0.9991486. Okay. I mentioned there were two main assumptions. That was one of them. The other is constant force of mortality. Here, you assume mu sub x is a piecewise constant. That is, the force of mortality is a piecewise constant, not the absolute death probability. Here, so if you want to, I said mu sub x is piecewise constant, so over that 1 year I can just look at the constant mu. Well, what is that constant? It's going to be negative natural log of Lx plus 1 over Lx. Right? By going back to definition of force of mortality, I'd say, well, this is the fraction of the number of people who survived. I know that e to negative mortality has to equal that fraction. Okay, mortality has to equal negative ln of this fraction. And I get that for a fractional year, rather than doing a what's called an arithmetic mean, you get a geometric mean. Which, if you don't know what that means, it's just, you say that L sub x plus epsilon is L sub x to the power 1 minus epsilon times L sub x plus 1 to the epsilon. And you can sanity check that. You could say, all right, if I wanted to know the number of people who survive, say, halfway into the year, assuming constant force of mortality, I'd have to say that the survival probability has to be the square root of the survival probability for the full year. Right? So when I take 2 half years next to each other, I have to multiply the survival probabilities together. I multiply the square roots together. I get the original survival probability. And then lastly, the other formula that should be intuitive to you, well, maybe. Hopefully you remember this from exam P. Epsilon qx is just e to the negative mu epsilon. Right? Locally, just in that fraction of a year, we model the number of survivors as an exponential. And this is what we get. Right? Okay, sorry about that. I just fixed a typo that you probably saw before. P sub x equals e to the negative mu epsilon. Or epsilon px equals e to the negative mu epsilon. Yeah, if you were looking at that 30 seconds ago and scratching your head saying, well, wait, this doesn't seem right. Yeah, it wasn't right. I made a mistake. This should be p sub x. Obviously, if epsilon is really, really small, you should have like a nearly 100% chance of surviving 1 second. Not a nearly 100% chance of dying in 1 second, which is what's going to happen if epsilon is tiny. Moving on. So if I want that same fractional age assumption using constant force of mortality, now instead of doing that linear interpolation, I have to do exponential interpolation. I have to say that the number of people who survive to age 30.2 is survivors to age 30 to the 0.8 times survivors to age 31 to the 0.2. And something similar with ages 32 and 33. So here are the formulas. Glance at them for a while. Do the algebra. And you get almost the same answer, 0.9991484. Shouldn't surprise you that you got almost the same answer. You were using the same data. Just slightly different reasonable approximations for what happens in between whole years. One thing that is reasonable to try to ask is which leads to a higher calculated survival probability. It's not that simple. It isn't that one function is more optimistic than the other. The comparison you'd have to make is that, so we know that after whole numbers of years, they have to be in agreement. So one can't be consistently more optimistic than the other. But UDD has a level number of deaths per year. CFM has more deaths earlier in the year and fewer deaths later in the year, which means comparatively it's as if UDD has more deaths. So UDD has more deaths than CFM does later in the year. And so if you're going from a end of whole year to a fractional year, then UDD is more optimistic. If you're going from a fractional year to a whole year, CFM is more optimistic. There's one more major topic covered in Chapter 3. Select lives. As I mentioned in Chapter 1, to qualify for insurance, for life insurance, you typically have to pass a physical. Make sure that there's not a strong possibility of imminent death. What this means is that if you just qualified for insurance, your mortality is slightly lower than somebody who qualified for insurance 20 years ago, but who knows whether or not that person started developing a major smoking habit over the past 20 years or something. And the way this is handled is that we have what's called a select period. Usually you'll assume that over a period of between 1 and 3 years is what I've seen on LTAM. That between 1 and 3 years, shortly after you've been approved for insurance, your mortality is modeled as being slightly lower. And the symbol for the age at which you were approved for insurance is that the age at which you were approved for insurance is put in brackets. So if a 58-year-old was just approved for insurance right now, we say bracket 58. So P bracket 58, or P selected at 58, is the probability that a selected just approved right now, 58-year-old, survives the year. Whereas if you were selected 20 years ago, right, it would be P no brackets, 58. Right? 58 without brackets. Now, I mentioned that there's typically a like 3-year window. And obviously you don't go from, better mortality, better mortality, better mortality the first 3 years to suddenly, oh, you're all the way back at normal now. No, it generally slides in a little more smoothly. How do you handle that in the notation? So suppose it's a 3-year period, 3-year select period, and you were selected 2 years ago. So you were selected at age 58, and you're now age 60. We can't say bracket 60 because you weren't selected right now. Your mortality is probably going to be slightly higher than someone who was just selected right now. However, we also can't say P selected at 60 because, yes, you were selected, but you weren't selected right now. So we can't say P selected at 60 for that reason. We also shouldn't just say P60 because it's not like you were selected 20 years ago. So what do? We say P selected at 58 plus 2 more years. That means this person is 60 years old now. 58 plus 2 is 60. But we say you were selected at age 58 and then 2 more years passed. So as an example, suppose I give you a select life table. How would you read a select life table like this? One thing I'll point out is that this so this is actually a table selected from one of the problems, one of the SOA problems for Chapter 3. And what I was going to point out is that there's some confusion about how to read the table because of confusion about how something like this would be generated. So let's start with a simple case. Suppose that someone was selected at age 60. So we could come up with numbers. We could say if I started with a number of people age 60, then I could monitor them, see how many survived to age 61, then how many survived to age 62, then how many survived to age 63. After this 3-year select period here, I now say how many survived to age 64. That's just going to be this here. So you go across during the select period and down after the select period. The period when the select period is over is called the ultimate period. But something that confuses people, confused me when I was first learning this, is, well, wait a minute. I see how you can do that for 60-year-olds. Now, how do we know to put this 78,000 here? Sure, you could say, if I started with 78,000 61-year-olds, then I could monitor across and see, look, 70,000 people survived to age 64. But of course, you'd have to already know the mortality in order to know how many people to select for your sample for monitoring. That's not how this is done. They typically just do year-to-year stuff and do calculations. But you could say, if we did start with 80,000 people selected at age 60 and 78,000 people selected at age 61, we would expect there to be the same number from each cohort surviving to age 64. We only know that because the table tells us that. So, okay, you go across and then down. So, given the following table, find and compare P63, P selected at 63, P selected at 61 plus 2 years, and P selected at 62 plus 1 year. Notice these are all different probabilities that ask about somebody age 63 surviving to age 64. And then I also ask, what seems wrong about this table? At first glance, nothing seems wrong about this table. And I said I pulled this from an SOA problem list. So it would be weird if there were anything wrong with this table. But as it turns out, something kind of weird is happening. This table was constructed to ask one particular question, and I guess they either didn't realize or didn't care that you have some anomalies happening. Because when we crunch our numbers, if we want P63, that would just be 70,000 divided by 74,000. P selected at 63 would be 68,000 divided by 71,000. P selected at 61.2, sorry, selected at 61 plus 2 would be 70,000 divided by 73,000. And selected at 62 plus 1 would be 69,000 divided by 72,000. We crunch our numbers. Now, it should be that the more recently you were selected, the higher your survival probability is. That turns out not to be the case here. They correctly identified that P selected at 63 is greater than P63, but it should also be greater than P selected at 62 plus one more year, and it's not. And that should be even greater than P selected at 61 plus 2 more years, and it's not. So when they were coming up with this table for this one problem where certain probabilities didn't even need to be calculated, they seem to have overlooked that fact. So do note, typically these probabilities would be, as I've written them here, would be ascending. They're not, because they kind of made a mistake when they were generating the table for this one sample problem where they wanted to ask about something completely different. Now, of course, we can combine all this and start talking about stuff that involves fractional ages. So I see Q61 plus half a year and probability of dying within 4 years. And problem says to use uniform distribution of deaths. Okay. So that means, let's see, selected at 61 plus half a year. That would put you halfway between selection at 61 and selection at 61 plus 1 year. And to go 4 years further than that, that would put you halfway between ages 65 and 66. You're in the ultimate period now, because this 4 plus this 0.5 is 4.5, that's greater than 3. So you just be here, between 65 and 66, halfway between 65 and 66. So crunch the numbers, you'll get that your survival probability is 66,000 over 77,000, and your death probability is 1 minus that. Gets you 14.29%. That completely covers the content of Chapter 3. For homework, I would recommend that you go over go through the 13 sample problems from SOA's official problem list. There are 13 of them for Chapter 3. And as always, if you like the way I explain things and want to arrange private lessons, click the link in the description below. And until next time, this is Dr. Nighttime wishing you a good night.